All right, welcome to the second video here in section 6.6. We're talking about the definite integral and what it represents graphically, and graphically it represents the area accumulation under the curve. And when I say under the curve, we really mean between the function and the x-axis. I should say if, my integral is in terms of x. How do I know if it's in terms of x? Well, look at this last part of the integral statement where it says dx, dx, dx. That means all my values that we're referring to, particularly these values in the limits of integration are x values. So when I look for the definite integral value of number one here, I have a new graph. I have a trapezoidal picture, a figure, and then we have a semicircle. So those are things to keep in mind here. Sorry, I just want to make sure I'm doing the right one. So we're going to find the definite integral of h of x, new graph shown, from 0 to 4. So from 0, so from here to here. So we're looking for this shaded area right there. So what is that shape? Because if I can find the geometrical formula to find the area of this purple highlighted part, then we're done. Again, some people like to break this apart and they'll make like a long rectangle and a triangle and then put those two together. If you want to do that, you're more than welcome to do that because that is one way to find the area of the shaded region. However, you can think of it also as a trapezoid. It's a trapezoid that has two bases, base 1 and base 2, and then the height is the vertical length. So therefore, I'm going to use that formula. So remember what the formula was. The formula was 1/2 times the height times base 1 plus base 2. So now I'm going to put everything into its proper place. The height of this trapezoid is 3. Base 1, the top part, is 2 steps. Base 2, the bottom part, is 4 steps. And so I think I can find my area using that formula. 2 plus 4 is 6. Half of 6 is 3, and 3 times 3 is 9. But let's say you had broken this up into two pieces like this, right? So then this rectangle would be a 2 by 3, so that would be 6. And this triangle would be 1/2 base, 1/2 times 2 times height, which is 3, which is going to leave me with 3. And then those two together would give me the 9 that we got over here. So again, depends on how you look at it, what you feel comfortable using in order to figure that out. But you do need to remember your geometry formulas of finding area formulas. When I look at number two starts at a different spot. It starts at -2. So now I'm starting over here, and I'm going all the way to 6. Oh, I'm stopping over here. Well, the good part is this middle part we already know is 9. So all we need to do is figure out this triangle area, and then this quarter circle area, right? Because we were given a half circle, but this is half of that. So this is a quarter circle. So let's start with what we know. We know this middle part is 9. I don't know this pink part, but the pink part is a triangle. So this equals 1/2 base times height. Okay, plus the 9 that we already had in the middle there, plus the formula or the area of this quarter circle. Remember that the formula for a circle is pi r squared. So this would be 1/4 pi r squared. Well, what's the radius of the circle? The radius is 2, right? Either 2 up or 2 this way or 2 this way. The radius is 2. Cool frijoles. So therefore, when I add the area of the triangle, which is 3, plus the area of this trapezoid, which is 9, plus the area of this quarter circle, which if you do all of this stuff, 2 squared is 4, 1/4 of 4 is 1, so that's just pi, then your answer is going to be 12 plus pi. Not 12 pi, 12 plus pi would be the exact definite integral of h of x between negative 2 and 6. Okay, so far so good. So I'm not going to do number 3 because number 3 is kind of the same idea. Just be careful. You can try number 3 and know that it go from 2 to 8. So we start here from 2, and then we go all the way over here to 8. So there's this triangle and then the half circle area that you have to put together. But it's the same idea. I'd rather go on to the next one because the next one offers something that we haven't seen before. And that would be, well, there's two things. That would be a function defined as a definite integral. And then number 2, when I look at the graph now has part of it under the x-axis. And so when I talk about the definite integral being the area accumulation between the curve, the function, and the x-axis, like this would be area positive, and this is going to be area negative because it's under the x-axis. And then this accumulation over here, area accumulation, is positive. And so I got to be careful with where my shading is. If it's under the x-axis, I got to treat it as negative accumulation. And I have to, even though I can find the area using the area formula, my accumulation, my definite integral value is going to be negative if it's under. However, let's go back to this, the way these are phrased here. It says the graph of f of x is shown above. If g of x equals the integral from 1 to x of f of t dt, can you find the following values? Okay. Well, g of 2, let's change colors here. G of 2 is what they want, but according to the formula, g of any x value is equal to the integral from 1 to that x value of f of t dt. Okay, so what does this mean? This means that I'm supposed to look at the graph of f. Oh, this is the graph of f. And I'm supposed to look between 1 and 2. Oh, between 1 and 2. Between 1 and 2, that would be this area here. So if I can find the area of this little triangle, I just found g of 2. So notice we're defining a function, g of x, by using a definite integral of f, a different function, right? But as long as you follow what the definition says, you're pretty good to get the idea. All right, so how do I find the area of this? That's a triangle, so it's 1/2 base times height. So that's just 1/2. Done. Okay, seems pretty straightforward. Let's go to number 2, g of 6. G of 6, according to this definition, g of any x value is equal to the integral from 1 to that x value of f of t dt. Okay, so now I'm going from 1 to 6. So I'm starting here, but I'm going all the way over here. And now I have to worry about this negative accumulation. So this equals the area that I found in green, which we said was 1/2, minus this area in pink. And I'm subtracting it because it's under the x-axis. So negative accumulation will occur for any area that's shaded under the x-axis, between the x-axis and the function. But this is a triangle, so that's 1/2 base 1, 2, 3, 4 times height 2. And if I do that, I believe, if I am doing things in my head correctly, I'm going to get 1/2 minus 4, and that's going to give me negative 3.5, or negative 3.5. Now, if you think about it, there is more pink area that's negative than green area that's positive. So when I put them together, I'm going to have a negative answer, right? Because there's more negative accumulation. This tells me exactly how much there is, negative 3.5. That's how much extra there is. Because the bottom part would be negative 4, the top part would be positive 1/2, and then subtract and you're done. Okay, this seems pretty straightforward. Let's do number 3. G of 1 is equal to the integral from 1 to 1 of the function f given. Well, wait a minute. If I'm starting at 1 and then I'm ending at 1, my limits of integration are the same. Am I accumulating or shading anything? No. So therefore, the answer to this is 0. So whenever my limits of integration are the same, that means my starting point and ending point are the same. I'm not accumulating any area because I'm not moving. I'm starting and ending at the same spot. My area, my integral value is always going to be 0. And then finally, number 4, g of 8. This will be the last one we do. So g of 8, according to the definition, is the integral from 1 to 8 of f of t dt. So let me talk about why these are not x's. We already have x as the function variable for g, so I can't use x here because then I would confuse this variable with this variable. So we use what's called a dummy variable, meaning that f of t could be any variable. It could be f of y, it could be f of z, it could be f of m. It's any number because the real variable of the function g is x. But because f of t and f of x use the same function f, it really doesn't matter which variable you use, right? But from 1 to 8. All right, so from 1 to 8. That means we're starting here, and we're going all the way over here. Here's the good news. We've already done most of the work. We just need to find this shaded part between 6 and 8, because we already have the green part, we already have the pink part, and we need to find the red part. So therefore, this g of 8 is the integral between 1 and 8. That means I need the first part, 1/2. I need the second part, minus 4. And now I need the third part, which is the area of this quarter circle. So 1/4 pi r squared, but my r is 2. My radius is 2. So then my final answer is going to be negative 3.5, which we already knew with the first two put together, plus 2 squared is 4. 1/4 of 4 is 1, so then therefore it's just 1 pi. This would be the exact value of g at 8 because it's the definite integral from 1 to 8 of the f function given. This is what we call accumulation functions, or functions defined by definite integrals. This is a pretty slick idea, and once you understand how it works, it's really not that bad. However, we're going to get used to defining some functions in terms of integrals, and we're going to use the second part of the fundamental theorem of calculus in order to find their derivatives as well. Anyway, excuse me. I think we found our 4 values here. And so we'll stop this video. We'll come back and we'll talk about what happens, what are some consequences of this.